Hello, chemists. Let's continue on with quantities. All right, today we're going to talk about the meaning of chemical equations. What does coefficient mean? What do the subscript mean? Now, I know we've talked about this in the past, but I really want to tie together today. And so, chemical equations, okay? What are those quantities? So, we are going to talk about those coefficients, and they can be interpreted as molecules or formula units. Remember, the only difference is one's a covalent bond, one's an ionic bond. They can be interpreted as moles, but they can also be interpreted as mass. So for instance, 1 mole of nitrogen gas is reacting with 3 moles of hydrogen gas to make 2 moles of ammonia gas, or 1 molecule, 3 molecule, 2 molecules. And the reason I said molecule is because it's a covalent bond. So I have molecules, I could have moles, but I could also say 28 grams plus 6 grams is going to give me 34 grams. Okay, it's all trying to tell us the same thing, although chemists prefer that one. Chemists prefer that one. All right, so the numerical relationship between atoms, molecules, formula units, moles, whatever. All right, I'm going to distinguish between inside and outside. If you are talking about inside a molecule, that is the number of atoms in one molecule. Or if we're using the term moles, it's the number of moles in one mole. Okay, one of them is just talking one, the other one is talking a whole bunch. So in one molecule of ammonia, okay, the little subscript 3 and the subscript 1. In a molecule, there's 1 atom of nitrogen and there's 3 atoms of hydrogen. But in a mole, there's a mole of ammonia. So there's a mole of nitrogen atoms. And there's 3 moles of hydrogen atoms. And it's all about the terminology. The math really isn't changing, but sometimes we can mess ourselves up by putting the wrong term. Now, what is the difference between inside for a molecule and inside for an ionic compound? Remember, you don't call it a molecule, you call it a formal unit, but it's the same thing. 2 atoms of sodium ion versus 1 atom of sulfide, or 1 mole makes 2 moles of ion and 1 mole of sulfide ion. All right, so that's pretty much the same. So inside tells you how many in each formula. Well, outside tells you how many there are total. And remember, if you're ionic, you'd say formula unit. Or if we're talking about moles, the moles total. So we have to be very, 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 very comfortable with our stoichiometry. All right. So if you're going to balance a chemical equation, in the past, you were just balancing numbers and ionic charges. I hope you got more out of it than that, but if not, here's a more in-depth explanation. So stoichiometry is a fancy way of saying, hey, they have to be at balance. What's their ratios to each other? So stoichiometric calculations inside, you must always start with a balanced equation. All right, you have to get the subscripts first. If you don't have correct formulas, there's no way you're going to be able to balance an equation. After you get the subscripts, then do the coefficients, and then you can use your recipe or your tool. So we're back to the stoichiometric dimensional analysis. So here is really the reason I made you do all of those stoichiometry problems, and more importantly, why I made you dig and say, oh, this is what I'm doing. This is what I'm doing, because I really need you to see when to use each part. All right, so here's how we're going to use it. Step number 1, do we have a balanced chemical equation? And the answer is yes. Once you get the subscripts fixed, don't touch them again. All right, then is it a balance as far as coefficients? And so this one is a balanced chemical equation. If I happen to start with 4 grams of hydrogen, what can I use? Okay. If I start with 4 grams of hydrogen, I could compare it to the ammonia. I could compare it to the nitrogen. I could compare it to many, 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 many things. We just have to have a stoichiometric relationship or a ratio relationship. And guess what? If I have a balanced chemical equation, I have one. So how many grams of nitrogen does it take to convert? If you're comparing reactants together, I'm asking which one's limiting. Okay, which one do you not have enough of? And we call that a limiting reagent or a limiting reactant. If you're comparing a reactant to a product, you're saying, hey, if nothing goes wrong, theoretical yield. If nothing goes wrong, what's the maximum I can make? And those are the two questions that we can ask. And so the one I asked here is, if I have 4 grams of hydrogen, how much ammonia could I make? All right, I'm going to go lower here. So the limiting reactant is the one that would be used up. In this particular question, I don't actually tell you how much of the other one I have. So I just set it up as 4 grams. Notice it's H2 because it's H2 gas. And so 2 times 1.00794. Chemists never compare grams of things. We always compare mole. What is the stoichiometric relationship between moles of hydrogen and moles of nitrogen? Okay, that's what you get from the equation. And it's 3 to 1. I'm no longer in moles of hydrogen. Notice I've also changed identity. I'm now in moles of nitrogen. And technically that's the answer, but I want to be in a unit that's a little bit more practical or a little more useful for me. All right, get rid of my moles of nitrogen and 2 times 14 because again, it is diatomic nitrogen. And it's telling me if nothing goes wrong. Okay, and I have 100% reaction, then the maximum I can make is 19 grams of nitrogen. Okay, assuming nothing goes wrong and it reacts 100%. Nothing escapes, nothing leaks out to the atmosphere. So this one is comparing a reactant to a product. So that would be considered the theoretical yield, the theoretical yield. All right, well, what if I have 2? Okay, so I'm going to do the same question, only I'm adding. Okay, let's see. I'm just going to make this number up. I'm going to add 3 grams of nitrogen with that 4 grams of hydrogen. All right. Do I have the exact amount? Do I have too much hydrogen? Do I have too much nitrogen? How am I going to tell? Well, I'm going to ask the math. And it does not matter which one you start with. Hey, math, if I have 3 grams of nitrogen, how much hydrogen do I need to use it all up? And chemists do not compare grams of things. So 28.02 grams of nitrogen in every 1 mole of nitrogen. Do you have a stoichiometric relationship between the two? Well, yes, my equation says that for every 1 mole of nitrogen, I need 3 moles of nitrogen. And the question has actually been answered. It's telling me how many moles of hydrogen I need, but I like to convert it into grams. So I know that for every 1 mole of hydrogen gas, there is 2.02 grams of hydrogen gas. So I asked, if I start with 3 grams of nitrogen, how much hydrogen do I need in grams? And then the math told me 0.6, how many six things do I get? 0.65. Let me do it again. So 3 divided by 28.02 times 3 times 2.02. Yep, 0.65. Okay, the math just said that if you start with 3 grams of nitrogen, you're going to need 0.65 grams of hydrogen to use it all up. Do I have that much? Yes. I have excess. I have more than I need. So who's going to limit? my nitrogen and limiting reagent or limiting reactant. Oh, okay. So which one would I use to figure out my theoretical yield? You always use the limiter. So now that I've changed that limiter, I'm going to say, hey, math, if I start with 3 grams of nitrogen, how many grams of ammonia can I make? And it says, oh, Joe, chemists do not compare grams of things. So I'm going to get back out. So 28.02 grams of nitrogen for every 1 mole. Do you have a relationship between nitrogen and ammonia? Well, in this equation, yes, it's 1 mole of nitrogen to make 2 moles of ammonia. But I don't want to be in moles. So for every 1 mole of ammonia, I'm going to make 14, 15, 16, basically 17.0 grams of ammonia. Grams of nitrogen are gone, mole of nitrogens are gone, mole of ammonia is gone, and I'm left with moles of ammonia. 3, 28.02, 2, 7, 3 point, let me see if it's 3.6. If nothing goes wrong, my 3 grams of nitrogen can be converted into 3.6 grams of ammonia. All right, so I have my limiter and I have my theoretical. Now, percent, you actually have to know. Okay, this is experiment. You go into the lab, you do this reaction, and how many grams do you really get? Okay, so I'm making this number up. I made 2.3 grams of ammonia. So the percent yield is basically how good did I do. So you take your actual, you divide it by your theoretical. Let me multiply it by 100. In this case, ooh, 63%. Now, some reactions were clear down in the 5, 10%. Okay, those aren't awesome reactions, but in graduate school, some of mine were like that. In inorganic, the one that you're in, anywhere from, I don't know, 60 to 90, 40 to 90. You can't really get any reaction to go 100%. And you're always going to lose some to the glass. You're going to lose some to filter paper. There's always areas of loss. But can you get over 100%? Well, sure, but not from your reaction. What would some of the errors be for that? Well, what if it was still wet? What if there was still solvent in it? You're not just weighing your product, you're also weighing the solvent. What if there's unreacted starting material? Well, you would be weighing your product and the unreacted starting material. So there's quite a few ways to get over 100%. So if you get over 100%, ooh, stop and go, what are my most likely possibilities? Check your math first. But occasionally you do, but it's not because you made more than that. It's because you're measuring something you didn't expect to. Okay, just wanted to show you a little thing that one of my past students gave me. All right, this is on your reference sheet. Some of you it's for the pink pages, some of you it's on the green pages. Now, never use a shortcut unless you understand why it works. But a nice little nifty thing is if you want to get between grams, molecular weight, and moles, remember formula weight if it's a ionic compound. If you're given the grams, you would divide by the moles to make molecular weight. If you wanted to find the moles, you would divide the grams by the molecular weight. If you wanted the grams, you would multiply the molecular weight times the moles. And we haven't done this one yet, but it's coming up. It's the same idea. Here, it's a little, I think, a little bit more visual. If you have grams and you want to get to moles, you need to divide by the molecular weight. If you have moles and you want to get out to grams, you need to multiply. If you're in grams and you want to get to volume, you need to divide by density. If you're in volume and you want to get to grams, you need to multiply. If you're in moles and you want to get the number of particles, remember that's a big subscript thing, you want to multiply by Avogadro's. If you're in the number of things or particles, then you're going to divide by Avogadro's. These are shortcuts. If you do not understand why each of those are working and you can set up the dimensional analysis, you really need to go back and practice those, because a shortcut is only good in certain circumstances and you have to know when to use it. But I do like that visual. I really do like this visual. And yes, it is on your reference sheet for you. All right, let me see, just peeking. There's concentration. All right, I'm going to do an entire another video and I'm going to do a limiting reagent problem, but this time it's going to be with cookies. Do you have to watch it? No, but I will use the exact same ideas, but I will use a cookie recipe so that we're not thinking, what is hydrogen? What is nitrogen? Just a reality issue about it. Okay, until next time, Jolly out.